How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You are sitting at a desk right now. Maybe you are looking at a computer screen or driving a car or walking down the street with headphones in. Look around you. Everything you can see, everything you can touch, and everything you are made of shares one fundamental property. It is three-dimensional. It has height, it has width, it has depth. This is the rule of our reality. Objects occupy space. Even a sheet of paper, which looks flat to the naked eye, is a molecular mountain range thousands of fibers thick. If you were to zoom in on the smoothest polished steel, you would see canyons and peaks. Our universe is built on bulk. But what if I told you that for almost a century, physicists believed that a two-dimensional material was impossible, not just difficult to make, but physically unstable? The laws of thermodynamics suggested that if you tried to create a material that was truly one atom thick, a single layer of existence, it would crumble, it would vibrate itself apart, it would roll up like a scroll. It simply could not hold its shape against the chaos of the thermal universe. And yet, in 2004, inside a laboratory in Manchester, England, two researchers used a tool that you probably have in your junk drawer right now to break that rule. They didn't use a billion-dollar particle accelerator. They didn't use a high-powered laser. They used a block of graphite and a roll of sticky tape, and in doing so, they peeled back the curtain on a material that has been called the greatest discovery of the 21st century. This is the story of graphene. It is the strongest material ever tested. It conducts electricity better than copper. It conducts heat better than diamond. It is completely transparent, yet so dense that not even helium gas can leak through it. It promises to give us batteries that charge in seconds, water filtration that can turn oceans into reservoirs, and computer chips faster than we ever dreamed. But how does it actually work? How can something so thin that it is effectively invisible be stronger than steel? How does a single layer of carbon atoms defy the laws of physics that govern the bulk world? And why, if it is so miraculous, are we not living in the graphene age just yet? Welcome to First Principles. Today, we are going to look at the pencil lead in your hand and see the strongest substance in the universe. We are going to deconstruct the honeycomb lattice. We are going to walk the path of the electron. And we are going to find out what happens when the three-dimensional rules we live by simply stop applying. Let us start with the magic. And I use that word intentionally, because when you first look at the list of properties attributed to graphene, it reads like science fiction. If you were to take a single sheet of graphene, sticking to the thickness of just one atom, and you stretched it out to cover a football field, that sheet would weigh less than a single gram. It would be lighter than the air around it. Now, imagine you took that same invisible, feather-light sheet and you tried to poke a pencil through it. To break that single atomic layer, you would need to balance an elephant on the end of that pencil. That is the tensile strength we are talking about. It is 200 times stronger than steel. It is stiffer than diamond. It can be stretched by 20% of its length without breaking, making it flexible like rubber. But the magic does not stop at strength. If you shine a light through it, it absorbs only 2.3% of that light. It is almost perfectly transparent. If you run a current through it, the electrons move with an ease that makes copper look like a gravel road. It is the best conductor of electricity and heat we have ever found. So, naturally, when this material was isolated, the world went wild. We started hearing about space elevators. This is the concept where we drop a cable from a satellite down to Earth and ride an elevator into orbit. We never had a material strong enough and light enough to support its own weight for that distance. Steel would snap under its own gravity, but graphene could do it. We heard about bionic implants. Because graphene is carbon just like us, the body does not reject it. We could have neural interfaces that merge directly with our brain cells, conducting signals faster than our own nerves. We heard about desalinization, a sieve made of graphene with holes just big enough for water molecules but too small for salt could solve the global water crisis. It sounds like the ultimate solution to everything, the philosopher's stone of materials science. But to understand why this isn't just hype, and also to understand why you don't have a graphene phone in your pocket yet, we have to go back. We have to look at the problem that existed before the solution. The story really begins with the element carbon. Carbon is the Lego block of life. It is the fourth most abundant element in the universe by mass. You are made of carbon. Your food is made of carbon. The wood in your desk is carbon, and the diamonds in jewelry are carbon. But here is the puzzle. Diamond is the hardest natural material known to man. It is transparent and brilliant. Graphite, the stuff in your pencil, is also pure carbon. But graphite is soft, gray, opaque, and greasy. It crumbles when you touch it. How can the exact same atom, arranged in the exact same universe, create the hardest substance and one of the softest? It comes down to geometry. In a diamond, each carbon atom is bonded to 4 other carbon atoms in a rigid 3-dimensional pyramid shape called a tetrahedron. It is a fortress. Every bond is locked down. There is no wiggle room. Graphite is different. In graphite, the carbon atoms are not locked in pyramids. They are arranged in flat sheets. Imagine a sheet of chicken wire, that hexagonal pattern. Now stack millions of those sheets on top of each other. That is graphite. For decades, scientists knew this structure existed. They knew graphite was made of layers, and they gave the individual, single layer, a theoretical name. They called it graphene. But here was the catch: it was purely theoretical. In the 1930s, brilliant physicists like Lev Landau and Rudolf Peierls argued that strictly 2-dimensional crystals were thermodynamically unstable. The theory was that if you had a 2D sheet, the thermal vibrations of the atoms at any temperature above absolute zero would cause the displacement of the atoms to grow immense. The sheet would ripple and crumble. It would lose its crystalline order. It would essentially melt. So, the consensus in the scientific community was clear. You can have thin films on top of something else. You can have multi-layers. But you cannot have a freestanding, single-atom thick material. It is a physical impossibility. Nature abhors a vacuum, but apparently, nature also abhors a flat plane. This was the state of the world in the early 2000s. We had silicon for our chips. We had steel for our buildings. We had carbon fiber, which is just graphite mixed with epoxy. But the holy grail, the single layer, was considered a dead end. Enter Andrei Geim and Kostya Novoseliv. These two physicists were working at the University of Manchester, and they were not your typical stuffy academics. Andrei Geim, in particular, had a reputation for curiosity-driven weirdness. A few years prior, he had won an Ig Nobel Prize for magnetically levitating a live frog. He was interested in poking the universe to see what happened. They had a tradition in their lab called the Friday night experiments. This was dedicated time to try things that were not in the grant proposal. Things that were maybe a little silly. Things that had a high chance of failure but a high potential for fun. One Friday, they were interested in graphite. They wanted to see if they could make it as thin as possible, perhaps to study its electrical properties. They tried polishing it. They tried rubbing it. It wasn't working very well. Then, a colleague mentioned how they used to clean the surface of graphite samples for microscopy. They would use everyday sticky tape. They would put a piece of tape on the graphite block and rip it off to remove the top layer of dust and grime. Geim and Novoselov looked at the used tape. There were gray flakes of graphite stuck to it. They wondered, if you took that tape and you folded it over on itself, sandwiching the graphite flakes, and then pulled it apart, you would split the flakes in half. You would have thinner flakes. So they did it. They stuck the tape to the flakes. They pulled it apart. They did it again, and again, and again, just peeling tape. It was manual labor. It was low-tech. It was tedious. Eventually, the gray flakes became thinner and thinner. They became transparent. They transferred these invisible flakes onto a silicon wafer so they could see them under a microscope. When they looked, they saw something that shouldn't exist. They saw a single, continuous layer of carbon atoms. It hadn't crumpled. It hadn't rolled up. It was sitting there, flat and stable. They had used scotch tape to disprove 70 years of theoretical physics. Now we have to open the box. We have to ask the hard question. How? How did they not just create it, but how did it survive? And more importantly, what gives this single layer its godlike powers? To understand this, we need to leave the world of tape and pencils and dive down to the quantum level. We need to look at the carbon atom itself. Let's go back to first principles. A carbon atom has 6 electrons. 2 of them are tucked away deep near the nucleus, holding tight. They don't do much in terms of bonding. The other 4 are on the outside. These are the valence electrons. They are the hands the atom uses to hold onto its neighbors. In a diamond, as we said, the carbon atom uses all 4 hands to grab 4 other carbon atoms. It is a 4-way handshake. Everyone is occupied. But in graphene, the carbon atom does something different. It undergoes a process called sp2 hybridization. I know that sounds technical, but visualize it like this. The carbon atom decides to use only 3 of its hands for structural holding. It reaches out to 3 neighbors. If you have 1 atom in the center, and it reaches out to 3 others equally spaced around it, what shape do you get? You get a triangle. And if those atoms reach out to their neighbors, you form a pattern of repeating hexagons. Think of a bathroom floor tiled with hexagons, or the cells of a beehive. This honeycomb lattice is the secret to the strength. The triangle is the strongest shape in engineering, and the hexagon is essentially 6 triangles meeting in the middle. When you pull on graphene, you are not pulling on a random jumble of atoms. You are pulling on a geometric grid that distributes the force perfectly across the entire structure. The bond between these carbon atoms, the sigma bond, is one of the strongest in nature. Because the atoms are so small, they can get very close to each other. The closer they are, the tighter the bond. So, you have this sheet of chicken wire made of the strongest bonds possible. But wait, I said carbon has 4 hands. It has 4 valence electrons. We have only used 3 to make the honeycomb. Where is the 4th electron? This is the key to the conductivity. This is the magic. The 4th electron is not used for holding the structure together. Instead, it is allowed to wander. It hangs out above and below the flat sheet. These free electrons form what is effectively a cloud or a sea of negative charge hovering over the lattice. In most conductors, like copper, electricity is a flow of electrons. But the electrons in copper have a hard time. They are constantly bumping into the copper atoms. They are scattering. It is like trying to run through a crowded room. This bumping creates resistance. It generates heat. That is why your laptop gets hot. In graphene, something profound happens to that fourth electron. Because of the unique hexagonal symmetry of the lattice, the quantum mechanics of the electron changes. Usually, we think of an electron as a particle with mass. It has weight. It has inertia. To move it, you have to push it. But in graphene, the electrons behave as if they have no mass at all. They become what physicists call Dirac fermions. The interaction with the honeycomb grid cancels out their effective mass. Imagine the difference between pushing a boulder up a hill and shining a laser beam. The boulder is heavy, it struggles. The light is massless, it just moves. The electrons in graphene zip through the lattice at speeds reaching a significant fraction of the speed of light. They don't bump into the carbon atoms because the path is perfectly smooth for them. This is called ballistic transport. They are not running through a crowd. They are driving on an empty superhighway. This is why graphene conducts electricity better than copper, and it is why it conducts heat better than diamond. Heat is just vibration. In that stiff, light lattice, vibration waves can travel incredibly fast without dying out. So, we have the strength from the triangular sigma bonds. We have the conductivity from the delocalized, massless pi electrons. And we have the transparency because the sheet is so thin that light simply passes through the gaps in the chicken wire, interacting with those electrons just enough to be seen, but not enough to be blocked. But I still haven't answered the first question, the paradox. How does it exist at all? Why didn't the thermal vibrations destroy it, as Landau predicted? It turns out the theory wasn't entirely wrong. It just missed a loophole. Graphene is not perfectly flat. If you look at it on a slightly larger scale, it ripples. It has tiny waves, like the surface of the ocean on a calm day. These ripples allow the material to accommodate the thermal vibrations without breaking apart. It ripples in the third dimension to save itself in the second dimension. It cheats the laws of physics by not being strictly mathematically two-dimensional in the way the old theories assumed. It uses the third dimension just a tiny bit to survive. So, we have opened the box. We see the honeycomb. We see the massless electrons. We understand the strength. It seems like we have the perfect material. We should be replacing silicon chips right now. We should have transparent phones and supercomputers in our contact lenses. But we don't. And this brings us to the unseen giant, the principle that is often left out of the pop science articles, but is the single biggest hurdle to the graphene revolution. The problem is not that graphene doesn't conduct electricity well enough. The problem is that it conducts electricity too well. To understand this, we have to look at how a computer works. At its core, a computer is a collection of switches, transistors. A switch needs two states, on and off, 1 and 0. Silicon is a semiconductor. That means we can control it. We can make it conduct electricity, and we can make it stop. We can create a gap where electrons cannot flow. This is called the band gap. Think of the band gap like a drawbridge. When the bridge is down, traffic flows. That is the on state. When the bridge is up, traffic stops. That is the off state. By flipping the bridge up and down billions of times a second, we do logic. We do math. We run the internet. Graphene has no band gap. In its natural state, graphene has what is called a zero band gap. The bridge is always down. The electrons are so fast, so free, and so massless that you cannot stop them. If you made a computer chip out of pure graphene, you could turn it on. It would run incredibly fast. But you could never turn it off. The current would just keep flowing. it would leak everywhere. The chip would consume enormous amounts of power and wouldn't be able to distinguish between a 1 and a 0. It would just be a constant screaming 1. This is the great irony of graphene. Its greatest strength, its conductivity, is its greatest weakness for computing. Scientists have been trying to fix this for 15 years. They try to cut the graphene into tiny ribbons to force a gap. They try to contaminate it with other atoms. They try to squash it. But every time you do that, you disrupt the perfect honeycomb lattice. You introduce bumps in the superhighway. The electrons get mass again. The magic fades. You ruin the very properties you were trying to harness. This is why you see graphene in tennis rackets and running shoes today. In those applications, we are using the mechanical strength. We don't need to turn the strength off. It is easy to mix graphene flakes into a polymer to make it stronger. But the high-tech revolution, the graphene processor, that is stalled by the band gap problem. We have the race car, but we haven't invented the brakes. However, the story does not end in failure. It ends in a new beginning. Because in the process of trying to solve this, scientists realized something profound. Graphene was just the first. It was the first two-dimensional material we found, but it is not the only one. There is a whole periodic table of 2D materials. There is hexagonal boron nitride, which looks like graphene but is an insulator. There is molybdenum disulfide, which is a semiconductor and does have a band gap. We have moved from the discovery of a single material to the invention of a new kind of engineering called van der Waals heterostructures. Imagine you are making a sandwich. You take a slice of graphene bread, you put a slice of boron nitride cheese on it, maybe some molybdenum ham. You stack these single-atom layers on top of each other. Because the layers are so thin, they interact quantum mechanically. You can design materials that do not exist in nature. You can combine the conductivity of graphene with the switching ability of other 2D materials. You can create a material that is custom-built, atom by atom, to do exactly what you want. We are no longer just digging materials out of the ground and asking, what can this do? We are acting like architects. We are saying, what do I need? And then building the material to match. So where does this leave us? We started with a piece of tape and a pencil. We found a material that defied the theoretical physics of the 20th century. We found a lattice that makes electrons think they are light, and we hit a wall because the material was too perfect to be controlled. But the real legacy of graphene might not be graphene itself. The legacy is the realization that the two-dimensional world is open for business. We have stepped out of the bulk, three-dimensional thinking that defined the Stone Age, the Bronze Age, and the Silicon Age. We are entering the Carbon Age, or perhaps the Flat Age. It forces us to reconsider what material even means. For all of human history, a material was something you held. It was a chunk, a block, a liquid. Now a material can be a single plane of existence. We learned that when you take away the third dimension, the rules change. Mass disappears. Strength becomes infinite relative to weight. The impossible becomes the standard. And to think it was hiding there the whole time. Every time a child drew a picture with a pencil, they were shedding microscopic flakes of the strongest material in the universe onto the paper. It was right under our noses, or rather, right under our fingertips. We just needed the curiosity to take a piece of tape, peel it back, and look. That is the power of first principles. It teaches us that the world is not exhausted. The fundamental truths are not all known. Sometimes the biggest breakthroughs don't require more complexity. They require us to strip everything away, layer by layer, until we are left with one single vibrating sheet of truth. The next time you use a pencil, take a moment. Look at the gray mark on the paper. You are looking at the wreckage of a million layers of graphite. But somewhere in that mess, hidden in the chaos, is a single perfect hexagon that holds the key to the future.
You've been listening to First Principles. Until next time, stay curious.